Welcome back to another of these sessions in which we're going to dive quite deep into the world of diode laser technology. I'm not reviewing products. I'm just personally trying to acquire knowledge about this 455 nanometer technology. Now, 450 nanometer technology doesn't mean to say I'm trying to just find out how fast and how deep a diode laser can cut. That's not technology, that's just experimentation with a few parameters and finding out what the designers of these heads have actually done to make it do such things. Now, I've invested in this 40 watt head myself. I hoped and thought that it may be able to do certain jobs that the CO2 laser struggles with. This should be able to do it better because it is PWM controlled. In reality, I've finished with this head. It means nothing to me now because I've already established that it is just not suitable for the purposes that I need. It's not a laser beam, it's 8 individual laser beams which have got strange properties. There's only one lens because only one lens can work with those 8 laser beams. They have to be set up through that one lens to coincide at a single point. Now that single point is not the focal point. That happens to be the point of coincidence of 8 focal points from 8 laser beams. And at that point of coincidence, there's all sorts of interference of light, which causes variation in the power output at the, let's call it focal point or the focal spot. It's not a focal point. I want to drive that point home to you. It's a point of focal coincidence of 8 separate laser beams. That means I have got zero flexibility of playing with the lens. I haven't just got one possibility with the CO2 laser, I've got endless possibilities. Well, I say endless, let's just have a look at it. I've got 3 materials for the lenses, 3 different refractive indexes. I've got 2 different shapes of lens. I've got a plano convex and a meniscus lens, so that's already 6 combinations. I can use the lens either way up or down, so that's 12 combinations. And I've probably got about 6 different focal length of lenses that I can use. So that's what? 72 endless options, as I said, for playing with the way in which you control the intensity of the beam hitting the material. This is a non-starter as far as I'm concerned. It's very restrictive, both in its capability and in its ability to damage materials. At 455 nanometer light wave, there are very few materials that actually truly respond at that light wave frequency. It has virtually zero effect on wood. Yes, it looks as though it's cutting, yes, it looks as though it's engraving, but it's doing that by pre-marking the surface by scorching and gradually producing a little puddle of carbon. That little spot of carbon then accepts all the light energy and converts it into kinetic heat energy, which then damages the material underneath. So there's a continual process of creating carbon and evaporating carbon, creating carbon, evaporating carbon to make this cutting effect that appears in wood. Carbon is a very important ally of diode laser technology, as I have found out. We will demonstrate that process hopefully in this session. I wanted to make this session all about titanium dioxide and basically the Norton white tile method. The widening of this session today was brought about by me watching a video about 8 different ways to engrave glass. And it's a very good video that you can watch for yourself on a channel called Laser Channel. Everything about that session was great, except there weren't any answers other than this method seems to give a slightly better picture than that method. Without being rude to people, that's the general approach that most diode laser users have. They find something that works and they use it. They don't need to know why it does it. They're not interested. That's the difference between them and me. I'm just eternally curious, want to suck in knowledge and understand how things work. Although I'm not going to repeat the tests that were done on this video, I'm going to use it as the basis for exploring some of the materials that were being used to engrave glass. Now, the problem is you can't engrave glass with a diode laser. It's transparent. All the light energy passes right the way through. You cannot damage the glass. Therefore, the only way that you can damage glass is to add some mechanism that absorbs the light energy and converts that light energy into kinetic energy, which vibrates the molecules and makes them hot. So you need a transfer film of some sort. And that's what these 8 methods of engraving glass were all about. Different ways in which you can convert light energy into heat energy to damage the surface of glass. In this session, we're going to take that quite a lot further and explore the results and why those results. Now, in these bags, I've mixed up some liquid. It's probably paintish consistency. I'm trying to get and find a way of making powders into paint-like substances that I can get onto the surface of tiles or glass. I've tried to spray things like titanium dioxide onto the surface of materials, and it's very difficult to get a powdery substance into a form that spreads nice and easily onto a material. So look, here we've got 3 white painty materials and 1 black painty material. Very crudely, I've put these materials onto a piece of glass. Some have gone on fairly well, some are absolutely junk, but that doesn't stop me from using them for my experiments today. We're not trying to produce high quality images. All we're trying to do is find out what the properties of these materials are when it comes to firing 450 nanometer light at them. So we've got materials A, B and C. We're going to look at material A. You see there is a film there. That started out as white paint, let's call it. We'll talk about what it actually is in a minute, but it looks like white paint. And this was not white, this was black, obviously, to start with. I'm not going to waste huge amount of time and glass acreage on some exotic test. I'm going to get straight to the bone and find out how this material reacts to this light with a very quick, simple test. I'm running this test at 400 millimeters a second and 60% power, which in your terms it's 24,000 millimeters a minute. I've just examined that pattern under my little eyeglass and there's nothing there. In a strange sort of way, I'm hopeful it has no effect on the light passing through it. And I see no hint of the pattern that I'm expecting to see. That's good news. We'll carry out the same test on the black material. And this time you should see, I hope, some sparkling on the surface of this material and not down here on my metal base plate. And there we go. We saw the flashes on the top there, not at the bottom. So that means that material there is absorbing the light. Have we done any damage? Now just there, you can't see it, but under my microscope I can see exactly what I'm looking for. So let's just set the focus up. I think we had it set to 7 millimeters for stainless steel. So let's go to 8 millimeters and see if I can get better focus. Now, this is at 100 millimeters a second, remember, and I'm pretty damned impressed with that in terms of the quality of the image that I've produced. I'm absolutely surprised that this machine is capable of doing that. Let's go to 200 millimeters a second. Now, 200 millimeters a second is too fast, but I could also put the power up to 100%. You heard that really burning, and actually that's done a half decent job at 200 millimeters a second. Let's go and have a look under the microscope and I'll show you what I'm looking for. That's the program that I sent down to the material. This is 254 ppi. Each one of these dots here is a 0.1 square pixel. So these are 0.1 with 0.1 spacings between them. So effectively, this is like a measuring grid. If I can produce dots that are the same size as the pixels, then I'm ready to do photo engraving. And we've got different size dots here with different spacings on them to check out things like the response time. And then we've got this pattern of dashes across the top here, which helps us to set the focus, because we try and set these to as thin a line as we can possibly get. And then we start concentrating on the speed and the power to get the definition into these dots. Okay, well here we are at the microscope and we're looking at the success or failure of the first test that I did. Now I must remind you that what we're trying to achieve here, we're trying to find materials that will react with or absorb 455 nanometer light and convert it from potential energy into kinetic energy, which is effectively heat, that will in turn damage the material upon which it's contacting. Now this first material was actually PVA glue. I diluted it with a ratio of 1:1 of water to make it into a nice silky smooth paint. But when that paint dried, it dried into a semi-clear or translucent material. And what we're looking at here on the screen is the surface of that material. You can see the little teeny weeny like droplets or blobs in the surface of the material. That's on the surface of the glass. And what I've got underneath the glass is a black line on a piece of white paper. It turns out that PVA glue has no effect at absorbing 455 nanometer light. The light just passes straight through like a piece of glass as though it wasn't there. So you could regard test A as a failure. But I'm a very positive person and look at it in a different way. It was a tremendous success because what it did mean is I could use PVA glue as an invisible agent to mix other powders into to produce a slurry or a paint which would attach to the surface of my glass. So that's what I did for the next test. I basically took some carbon black, which I suppose would be regarded as posh soot. It was micro granules of carbon. I had great difficulty in getting the carbon to mix with the PVA glue, and if I move the lights around you'll see what I mean. This looks just like the surface of the moon. So for the purpose of what I'm trying to achieve, this is fine. We're not trying to produce superb quality engraved images on glass. Instead, what we're trying to achieve with this is to prove that this material can absorb 455 nanometer light and convert it into heat. So there's one of our first tests, and as you can see, this is an upside down version of my pattern, and you can see the dashes, we can see the central line of dots, and we can see the pattern of very small dots along there. So this is not bad, it's nearly there. So when I get the light set just right, you can see with shadows in here as though this is, these are craters on the moon, and you can see it in the dots here. Now the other thing that you can see is around these dots we've got some sort of yellowy effect. That I believe some residue from the PVA binder that I'm using to fix these carbon granules to the surface. Now I found it very difficult to get a very smooth mixture when I tried mixing carbon black with PVA glue. I should have spent more time and used a mortar and pestle to grind this down into a super smooth mix. But hey, I didn't, and it doesn't really matter. The one thing that you can see here is we've got some grooves which we've burnt through the carbon, and if we look carefully you'll see just here we may be in just one or two places we might have damaged the glass. We can't just make that carbon disappear because we fired the laser beam at it. What we've done, we've made it what they call sublimate, which goes directly from solid to gas, but that happens at 3,500 degrees C. We must have had a very high temperature in here to cause that to happen. As soon as we burnt through the carbon, we don't get any heating effect on the glass itself.
So the laser beam is hitting the surface of the carbon and it's turning it to white hot 3,500 degrees C. What we're trying to do is to allow the carbon around this disappearing zone to heat up in advance of disappearing, such that it transmits its heat to the glass before it disappears. Now what we've just seen on the picture is not quite that. There's not been quite enough time to allow this heat to transmit into the glass and do damage. So we've got to understand what's actually going on at this micro level before we can make a decision about what we need to do to allow us to damage the glass. So the amount of heating you do at that point there is dependent upon the exposure time that you allow 40 watts to hit that material. And that exposure time depends upon two factors. Number one, the power that you're putting into the beam, because power is not really power, it's exposure time. So 50% power means you've got 50% on and 50% off, 40 watts. So that's effectively net 20 watts in the area there. And then in addition, you're moving across the area at speed. So the faster you move across the area, the less exposure time you're giving that particular piece of material to 20 watts. It becomes very complicated. And that's why people just look at the results. If they don't get the right results, it's a failure. And so we move on to something else and we try some different parameters. That's not my approach. I like to understand how and why so that we can make a logical decision about what's the next step.
So I put the speed up to 200 millimeters a second and the power up to 99%. You can see in the center here of these lines, we're now starting to damage the glass. I've managed to scrape away my moon dust. So the dots are around about 0.05, but they're not powerful enough. We haven't damaged the glass yet. So what we've got to do now is we've got to decrease the speed from 200 back to 100 with the power at 100% to see what damage we can do for these small dots. Now there are other things that we can play with my machine that you can't play with your machine. I'm not actually running this on Lightbird at the moment. I happen to be running this in RD Works. It doesn't make any difference which software I'm using. Basically what I've got this set up at the moment is as an RF laser, no pre-ignition, which means I'm using the PWM signal from my controller to control the diode laser head. And when I get to setting the parameters, I can go into advanced here, and at the moment I've got nothing set. You would have that set to 5 kilohertz. So I'm now going to drive the same pattern at 5 kilohertz and see what we get. So we want speed of 100 and I want the power to be 99. Okay, so now you should really hear it crackling this time and also see lots of blue light. Examine this with my little eyeglass and I definitely know that we've damaged the material now. So just a few quick tests. And I've already determined that this material works well. The white material is rubbish. But that's purely because I haven't really experimented with the mix quality at the moment. But let's just try that with the same settings. And I have to say, that's looking pretty good. This is titanium dioxide, and normally this would be powder, and you couldn't do anything with it. You certainly couldn't do this with it, but now you might just be able to see my little pattern there. So what I'm going to do, I'm just going to try and scrape that off with my fingernail, look, which I can, and I think you can probably already see. So here was my last and greatest carbon result. Scrape the carbon film away, and what we're left with is nice clear glass dots. First of all, we've got our boiling glass here. Now this sort of glass melts at about 1400 degrees C. For bubbles to form in the glass, and look, there are no bubbles on the area around it, this must have been heated above 1400 degrees C and more to boil it, because you don't produce bubbles in glass unless you produce a boiling liquid. So we've managed to transmit a lot of the 3500 degrees C from the carbon into the glass surface. And because it's happened at such a high speed, when it's cooled down, we've generated some shear lines here. Look, the glass has cracked. Now, in addition to that, if we take a look around, particularly the outside edge here, you'll see around here, you'll notice that we've got lots of little black inclusions. Well, I think those are bits of carbon that didn't get a chance to evaporate, and they've been included in the melted glass itself, right? And they've migrated towards the edge around this heat zone on the edge here. So let's go and have a look to see whether it's a constant with all the other dashes and dots. There's a fairly serious sheared result there, and yes, we've got inclusions in here, black inclusions. And we've got lots of bubbles inside the melt itself, which is going to scatter the light and cause it to look greyish, in the same way that fog looks grey because it's microparticles of water suspended in air. These are effectively microparticles of air suspended in glass. The opposite way around, but it has the same effect when light passes through it. As I've said many times before, our eyes only see averages. They can't see the sort of detail that we can see here under the microscope. So let's look at some of the dots. And again, we've got the same properties on these dots. Look, we've got migration of the blackness to the edge, and then we've got these shear lines. So this would indicate to me that we've got too much heat now. We've gone from one extreme to the other. And then we moved on to our other white substance, which was titanium dioxide. And with exactly the same settings, they're looking pretty good. Now, we've still got shear lines happening around here, but we have very little in the way of shear results on our dots. So titanium dioxide is transmitting heat into the glass in a slightly different way. So let's go and have a look at some of those dashes in more detail. And we see some rather interesting facts here. Number one, we've definitely got a big shear around here, and we've got cracks in the glass around here. We don't have as many bubbles in the central section. So it may be that it didn't get quite as hot in this zone here. So the transmission of heat to the glass is lower, but it's still nearly the same as carbon. So we found another material which is good at sucking in the 450 nanometer light energy and transmitting it into the material that it's fixed to. There's something very, very interesting at the edge of our hot glass bubbling. We note that we've got some black inclusions. Titanium dioxide is a white material. It's a very special and strange material. And very few people realise or understand how it is so successful with the Norton white tile method, i.e. you can produce black engraving on a white tile with a white material. But we'll talk about the science of how that happens later on when we get to the Norton white tile test. So the fact that we've got shearing on there means we seem to have too much stress or power going into those dots. So there's a balance between too much and too little power, and we haven't found the correct balance at the moment. Now, I can do something on my machine that you can't do on yours, and let me explain. We call these sessions a deep dive into laser technology for a very good reason, and that is exactly what we're going to do now. We're diving deeply into trying to untangle the problem of how we can get a less powerful dot without necessarily playing with the power and the speed. There are other things that happen in your diode head. For example, we've got 5,000 pulses per second on my 40 watt head, because you saw me set the pulse rate to 5 kilohertz, 5,000 cycles a second. And for this example here, what I want to do is I want to make the PWM signal 50% on, 50% off, i.e. 50% power, which means that we've got 40 watts on, 40 watts off, nothing. 40 watts on, nothing. So we've effectively, over that cycle, got 20 watts of effective power. We're running my test at 100 millimeters a second. And at 100 millimeters a second, we've got 5,000 pulses per second. So what that means is we're getting 50 pulses for every millimetre of travel. So the pattern that you've seen me working on is basically a 254 pixels per inch image, i.e. the pixels themselves are 0.1 square. And if my pixels are 0.1 square, it means I've got 10 of those pixels in a millimetre. But in a millimetre, I've got 50 pulses. So that means every pixel is going to see 5 pulses, not one pulse. Let me just redraw this again. So here we've got a square pixel that's black. And the controller says, okay, I've come across a black edge here. I need to switch the laser on. So it switches the laser on at that point there, where the centre of the beam is at that point. And of course, what's happened? I've got half a pixel outside where I need it to be. So I now go 5 pulses, and the last pulse happens to be on the other edge of the pixel, where that then produces another half a beam outside the pixel. So whereas we thought we'd got 1 pixel wide, we've actually got 2 pixels wide for 1 pixel signal. So that creates its own sausage-shaped pixels when we come to do photo engraving. We're not going to be able to put 1 dot on 1 pixel. Very simply, what that means is, for this image here, 254 ppi image, I've actually got to not put 5 pulses per pixel, I would like to put 1 pulse per pixel. And to do that, I'd have to run at 1 kilohertz, not 5 kilohertz. Now you can't change your PWM frequency, but I can change my PWM frequency. So we're going to run the titanium dioxide test again at 1 kilohertz frequency as opposed to 5 kilohertz frequency to see if we get any change or improvement to the quality of our dots. That was 90% power. I'm now going to run 70 and 50% power. And then we move on to 1000 pulses per second, and we did this at 90% power as opposed to 99% power, 5000. And you'll notice we haven't got as many bubbles in the center, so we've got a lot less power, and we have got probably slightly smaller shear patterns. There is black around the edge still, but you'll notice that they're much smaller particles. Again, we've got this problem. White powder, clear glass, where's the black coming from? Okay, there's a dash now at 70% power, and because the power is off for 30% of the time, it becomes much easier to see the individual dots. Right? Each one of those dots is a single pulse. It's not 5 pulses anymore. Even though that's a continuous line, it's a continuous line of single dots. So if we compare that to the single dots themselves, they're quite clean, those dots. Okay, so that makes a big difference when I drop that to 70%. Well, at 50%, so this is a dash, but it's a dash of individual dots. And you'll notice how the black spots are now more evenly displaced around each one of those. Now let's go and have a look at that really close up, shall we? Well, as we go up and down through the dots, you can see that some bubbles are there. We've certainly got a lot of little round dots, black dots. Where are those black dots coming from? I keep asking that question. So when we look at the bigger picture at 50% power, 1 kilohertz, we've almost made the dots disappear. So there's yet another mechanism by which we can control the burn on the dot itself. Now bear in mind, this burn is not happening to the glass, it's happening to the titanium dioxide on the glass, and what we're seeing is the result of heat being transmitted through the titanium dioxide, because the titanium dioxide itself is being evaporated. Titanium dioxide boils at say 3000 degrees C. Okay, so it has to boil and evaporate, whereas carbon just disappears, it sublimates. So let's stop for a minute and review where we are. We had total failure there with my carbon application because, as you can see, it's crusty, it's cruddy, it's the worst application ever. But it did serve to prove the point with my little tests here. Now that was a big failure. Now this was also possibly a big failure because that didn't absorb any energy. But on the other hand, that was a major success, because what it means is I can use this adhesive, this PVA adhesive, as a binder to pull all this stuff together. Carbon was particularly bad because I don't think carbon likes mixing with anything. We're going to have a go at trying to make a titanium dioxide mix. The first experimental tests that I did showed that I need roughly a ratio of about 2 to 1, or rather 1 to 1, 50% water and 50% glue, to give me a reasonable paint mix. Let's add about the same amount of water to it. Here I've got a Dremel powered rotating lump of plastic. Now the reason why it's on a stem is because I want the larger part of it to go under the fluid and the top part here to stay above the fluid so that it doesn't cause too much splashing. So what we'll do, we'll drop that in. I don't want it to run too fast, and as we mix it, it should get faster and faster and faster, and I can control the speed by touching it on the side and slowing it down.
So let's just take that out very slowly. Spin the fluid off before it gets a chance to throw everywhere.
So I've now got a pretty runny mixture. This is pretty lumpy. It's not uniform. That is about the same volume as what I've got in there at the moment. Something handy to stir it with to start with, because I'm not going to put my wuzzy thing in there at that speed. So let's get it a little bit into a slurry. But before we put any more water in it, what I want to do is turn it into a smooth consistency. I want to grind all the lumps out of it. I've got this on its slowest speed. So what we do, we'll drag it on the edge to slow it down. And then we'll put it into the mixture. And as soon as I put it in the mixture, the resistance of the mixture slows it down naturally. At the moment, look, it's far too gloopy. And there's still lumps in it. So we need to put some more water in it. How much? Well, we should have to just play with it. So I've mixed up some glue, titanium dioxide and some water in there to make a mixture which is pretty much like paint. So get plenty of it on. Well, it certainly spreads and feels like paint. Yeah, it's got that same drag that you get with a paintbrush. And that's obviously because of the glue that I've put in it. Just put a little bit more on the basis that if there's more, it may well spread out and even out like gloss paint does. And there we go. Now, it is slightly streaky up and down, like paint normally is. But I'll leave that for 10 minutes before I put that in the oven to dry. I pop it in the oven at about 60 degrees C and leave it for 10 minutes, and it's completely usable then. Okay, so here we've got another white material which I'm going to test to see whether it is capable of absorbing 455 nanometer light. The answer is yes, it does look that way because I've got some pattern on there. So I've painted this material on here with a backing of with acrylic glue base. So I should be able to just peel it off with my finger. The question is, have I marked? Well, it's done something, but not very much. This material doesn't look as efficient as titanium dioxide or carbon. So we've run this second test at 50 millimeters a second, and yes, we've definitely got a darker, clearer result. And if I scratch that away, you can probably see that we've got a positive mark there. I'll tell you what this material is in a second, but what you can see here is at the same settings that we were successful with on titanium dioxide, we've hardly marked this material. So this is not absorbing or transmitting the heat through to the glass as quickly as the titanium dioxide or the carbon. So we went down to 50 millimeters a second from this setting, which was 100 millimeters a second, in an attempt to increase the exposure time by 100%. We've got pretty good results. Let's zoom in and look at the dashes. And very interestingly, what we see is less stress cracking. So we haven't got too much heat causing this problem. But having said that, the energy is getting through very nicely because look, we've got bubbles in the center of the burn, and we've got thousands of micro bubbles around the outside of the burn. And those micro bubbles are going to have a great effect on engraving because they are going to catch the light, as I described before, like fog. And they're going to scatter the light and produce a lovely grey-white effect. This is actually would be better at engraving than the titanium dioxide. For normal scan engraving, this is going to be superb. For image engraving, where you use dithered images, we need to look to see what's happening to the single dots. And again, we can see that they have got lots of little micro bubbles in them. Something I hope you'll notice. There is no black around the edge of these bubbles. Just clear, clean bubbles. Let's go back to the dashes. And no matter which dash you look at, there is no black. Just clear bubbles and a few cracks. I've mentioned this before, but understanding how laser technology works extends way beyond the laser beam itself. You need to understand quite a lot about the properties of materials. And one of the interesting properties of materials that you ought to look at on the big Google thing is something called, what they call the absorbance spectrum. Now, the absorbance spectrum for titanium dioxide which we've already looked at, is here. And at 455, it stops being super to being just pretty normal average. Okay, but if we take a look here at CaCO3, which is calcium carbonate, and that is chalk, which we've just been looking at, you'll find that it's virtually the same absorbance capability at 450 nanometers as titanium dioxide. So why doesn't it perform the same? Because it's got the same absorbance capability of taking in the 450 nanometer light waves. So titanium dioxide boils at about 3000 degrees C and then evaporates. It's not far off the melting point of carbon, where carbon disappears into gas at 3500 degrees C. Whereas calcium carbonate, although it's got the same absorption capability, what temperature does it disappear at? Well, the answer is below here. Look, calcium carbonate decomposes at 825 degrees C, so it's about a third of the temperature. Still pretty damned hot, but then it decomposes to form quicklime, and this carbon content breaks down and evaporates as carbon dioxide gas, so it disappears. So the heating effect of calcium carbonate is a lot less violent than the dramatic heating effects of titanium dioxide and carbon. And that's what we're seeing in these pictures here. First of all, there is no carbon or black stuff in here, even though there's carbon in the material itself. That carbon disappears as carbon dioxide. It doesn't finish up settling around the edge here. So we've got a white powder which disappears, leaving a nice clean edge around here. But we had a white powder in the form of titanium dioxide which contains no carbon at all, and yet somehow we finished up with black particles around here. What's going on? Where does the black come from when you've got white powder? Well, look, underneath that nozzle there, I've managed to build a little pile of titanium dioxide. It's all compressed together. See, the problem now is the air assist is going to blow it all away. Let's see if we can just compress a little pile of it together so that it doesn't blow away. We've got a little piece there. Look at that. I think what I might do is take that and have a look at it under the microscope. Look, we've got cracks in the glass because I had this on a piece of glass. You'll also notice something else that's around here as well. We've got some black something or other. I'm going to try very carefully to peel away with this hypodermic needle, if I can, some of this crusty bit around the outside here. Now, unfortunately, this doesn't come out quite as positive as it did when I did the same experiment with the CO2 several years ago. Maybe what I'll do, I'll cut in a piece of video that shows you how I discovered exactly what was happening with titanium dioxide using the CO2 laser. Because I had several inquiries at that stage from guys that had got their diode lasers and wanted to move up to a CO2 laser and wanted to know whether the Norton white tile method worked with a CO2 laser. So I had to do some experiments to find out exactly what the Norton tile method was and why and how it worked. Is my titanium oxide that I used for engraving on a white tile. In that instance, what we have is a very, very finely ground white powder that started off life like a piece of coal. Black is total absorption of all the light. It's not transmitting any back at you. And white is reflecting all of the light back at you. So somewhere between when this was originally made and what they've done to it now, which is turn it into a very, very, very fine powder, the crystal structure of that material has changed so that it has got different light absorption properties. It's still the same material. Basically, that is still a black material. But black is not a colour any more than white is a colour. They just happen to be
different ways of reflecting the light. I'm going to have a go at burning that with the laser beam. I know what happens when I paint it onto a white tile and I heat it up. It turns black, because what it does, it starts to recombine all these micro particles that are in here back to what it was originally, like a piece of coal. This requires a very high temperature to make it turn into something else, but whether we should be able to achieve that, I don't know. So, what have we got here? Look, we've got a piece of coal. From white material, we've turned it back to what it was originally, black material. And that is how the Norton process works.
So here's what you've all been waiting for, the Norton white tile method. Well, this is not exactly the Norton white tile method. This is using titanium dioxide as opposed to Rust-Oleum paint, which was the original principle. Now, the first thing I've got to do before I do anything is to try and set the focus, the speed and the power. Because if you remember, we've already tested it on glass, but this is not glass. On the surface of this tile, we've got something different. We've got a glaze, which is not the same as glass. Glass has got a melting point of about 1400 degrees C. Glaze could be as low as maybe 1000 degrees C. So it's a completely different material. Now, although I'm going to start off with the same parameters, 1 kilohertz, 90% power, 100 millimeters a second, these might not be the correct parameters for this type of glass. And there's our little test pattern. Question is, what have we got underneath it? So I've looked at those with my glass, and the answer is they're quite nice marks, but they're not particularly black. So I think we will have a go at slowing that down to increase the exposure time. Right, so here comes the problem now. We've slowed it down. We've got blacker marks, but what we've also got is thicker lines, because in slowing it down, we've actually made the beam wider. So we've got to reset the focus now. So our first test there was at 100 millimeters a second, just to replicate what we've been doing before. So that's 1 kilohertz, 100 millimeters a second, and 90% power. I changed the focus to see if we could find a better focus. What I've done, I've made the dots bigger as well. So then we set the focus back to 9 millimeters, we reduced the speed. And in reducing the speed, effectively what we've done, we've increased the exposure time, which has in turn increased the beam width. And because the beam width has increased, we've also got an increase in the spot size up the top here. Those spots are now 0.22 diameter. I then pushed the speed up to 75 millimeters a second. And you can see the immediate difference. First of all, these are smaller. These are now probably 0.18 diameter, because there's just a hint of a gap between them. 25 millimeters a second has had a significant effect on the beam width. Now I want you to keep a note of this data, because it's very, very important, especially in the next session when I'm going to talk in more detail about the principles and the practices that people adopt for engraving. They're totally wrong, because they don't understand what happens to their beam as they change the speed and the power. The best compromise that I could come up with was 75 millimeters a second, 1 kilohertz, and the focus of 9 millimeters air gap. Those dots, they're probably 0.13, 0.15. They're not particularly small. I mean, this is a 254 ppi image. I haven't got very much in the way of blackness in those dots. Now the question is, why is it that some dots are black and others are not? Well, I think it comes back to the same problem that I identified when I was trying to produce colour. We've got variable power happening at the focal point, because we've got the coincidence of 8 laser beams that are not working together. Sometimes they're doing their job together, and sometimes they're fighting with each other. And here it looks as though they're doing the job together, and here it looks as though they're fighting with each other, because they're not producing the power that's required to make a nice black dot. It looks as though it would do a reasonable job if you were doing continuous engraving, line scanning, text, but not dithered images, because dithered images, it just can't handle the dots. This is just another good reason why I would never consider now using a diode laser, even though I thought a diode laser might be good for this sort of work. Now, there are just hints in here of what you can do with titanium dioxide. Let's look at that dot in particular, and I'll explain what you can do consistently on a CO2 laser that I can't do here with this diode. Here's the real magic of titanium dioxide. If the beam power is correct, you get a tremendous difference in the melting point of the titanium dioxide and the low melting point of this material, which is the glass which surrounds it. So around the outside here we've got a little patch of melted glass, and the melted glass has got a different surface tension to the titanium dioxide glob that's formed, and so the glob migrates towards the center of the dot, and so consequently, magically, you can produce black dots that are half the size of the nominal dot size that you're melting. That's what I'm hoping to see on every single dot. Is it there? No. No. There's a hint of it there. No, 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 no. Oh look, there's one there. So the point is, there is sufficient power there at times to be able to do what I expect it to do. But it's not there on every dot. That tells me that we've got varying power on every dot. And that's just not acceptable to me. It means I can't get consistent results. I mean, I've prepared very nice tile to do a demonstration on, but on the basis of these results, I'm wasting a very good tile, and I'm not going to even attempt it. As I mentioned at the beginning of this video, I'm not reviewing this laser tree 40 watt head. I'm reviewing diode technology and comparing it to fiber laser technology and CO2 laser technology. And I'm afraid this technology falls far short of the other two. Now, I might sound like a grumpy old man shouting at the moon. I've had several people ask me, have you shown us any real comparisons between diode technology and CO2 technology? Now, here's some of the very first dots that I ever produced with CO2 technology and titanium dioxide. I managed to get much better results than this. Now, photo engraving, which is what most people try to do, is not pushing the technology to its limit. I try and achieve photo replication. And to do photo replication, you must have one dot equals one pixel. If you throw the pixels away, as you do when you start modifying your picture by lightening it, sharpening it, changing the gamma, doing all those sorts of things, you are throwing away the subtle detail that's in the image. Now, here's a good example of what I was able to achieve at 200 millimeters a second with a 508 ppi image. I was able to replicate 508 ppi with 508 dpi using titanium dioxide. It was absolutely amazing and told me just how far you could push the technology to with a CO2 laser. Now just take a look at the detail in those lower eyelashes. Yes, you could achieve the same sort of detail if you had a picture that was this size. But this is not the size of the picture. This is just a small part of a much bigger picture. You do not get that detail in a bigger picture unless you've got the resolution in the basic image itself. It's jolly cold out here tonight, just above freezing, so I'm not going to stand around here too long. Now, I haven't quite finished all the testing that I want to do on glass because there's one material that I haven't tested that's still in the post to me. So we'll carry that on to the next session. Now, although I'm fairly confident that my journey with diode learning is coming to an end, I'm aware from the many videos that I've been watching from experts and enthusiastic hobbyists that there are many myths, misunderstandings and seriously wrong advice that's churning around like a washing machine on YouTube. I've learned lots of new things, but one thing I have learned is that diode lasering is not for me. In the next and final session, I hope to gift the truth to those many people that are persevering with their diode laser technology, because many of the so-called truths are far from. Thank you very much for your time and patience today, and I will catch up with you in the next session.